Chapter 6, Radiation and Cancer. This chapter covers sunlight and ultraviolet radiation, ionizing radiation, and other forms of radiation. The term radiation is used to describe types of energy traveling through space. So this is very, very high energy that we would be exposed to throughout our lifetime here on Earth. And due to this exposure to radiation, that can expose us to instances where we're obtaining mutations or DNA damage, and that will predispose us to developing cancer. So in Chapter 5, we had learned about chemicals that can form DNA adducts, and that DNA damage, if it's not repaired, can certainly lead to the development of cancer. And very likewise, if we're talking about radiation, if the radiation is causing DNA damage events, then that also will increase our rates of getting cancer. So we are exposed to radiation in our day-to-day lives here on Earth. We have radiation coming up from the core of the Earth, radiation coming in from the atmosphere. We also experience radiation if we're doing any medical exams, if we're doing x-rays, things like that. We have just various other small amounts of radiation in various equipment that we use, and also if we're flying, we're higher up in the atmosphere and we're exposed to some radiation up there. So we are exposed to radiation. Also, it's important to note that as humans evolved here on Earth, we have had to evolve in a situation where our bodies are exposed to radiation. Therefore, our bodies also developed DNA repair mechanisms at the same time, kind of in parallel to that, to help to handle all of those different DNA damaging events that are occurring on us at all times. One of the ways that we're exposed to radiation is through sunlight, and sunlight specifically gives us the ultraviolet radiation. So we do have 3 different forms of ultraviolet radiation: UVA, UVB, and UVC, which we'll be talking about later. And due to this exposure to radiation from the sun, we do experience a very, very high number of skin cancer cases. About half of the 1.3 new cancer cases in the United States are caused by the sun, or that are skin cancer. So this is our biggest numbers for the types of cancer. So skin cancer would be number 1. When we're looking at the graph that is shown here, we're looking at the graph of the United States, and it's showing you the sunlight intensity scale in the different states. And then we also have the cancer rates. We have some representative graphs from different regions of the United States. In the graphs, you're going to see 2 bars. The blue bar will be basal cell carcinoma. The purple bar will be squamous cell carcinoma. And so we're looking at those different cancer rates for those 2 types of skin cancer. So in states that have a lower amount of UV radiation coming in from the sun, we do see that their rates of cancer are lower. In states that have higher amounts of radiation from the sun, then we see that their rates are much higher. So it seems to correlate with the amount of, like sunlight, UV intensity in these different states. And we do see that the basal cell carcinoma, their rates are much higher than the squamous cell carcinoma, and basal cell carcinoma is the most common type of skin cancer. In this diagram, I just wanted to point out the layers of the skin and just discuss those different types of cells that these different types of skin cancer can arise from. So with the skin, we have a couple of different layers. We have our epidermis, which encompasses this area highlighted in green. We have the basal cell layer, which is at the bottom of the epidermis, and then we have the dermis. So the basal cells layer are at the very bottom. These would be those rapidly proliferating cells. And then as we look into the epidermis, we're going to see squamous cells here. And so if we're having basal cell carcinoma, they're coming from these types of cells. Squamous cell carcinoma is going to come from this upper layer. We also have melanocytes. These are specialized cells that can make melanin. So this is the pigment that's produced. And this pigment can help to protect the skin against the the damages from UV light. So the more exposure we have to UV, then the more melanin we could possibly make. So when we're talking about melanoma, this would be a type of cancer that comes from these melanocytes. This slide here is showing our melanoma detection scale, the ABCDE system. So I put this in our slide deck just because we didn't have a lot about skin cancer directly in our book. So I just was showing you what some of the detection scales are, just kind of for your general knowledge for yourself, and also so you can help to look out for various family members. And this is specifically talking about melanoma, whereas we've mentioned the other two kinds of cancer, basal and squamous cell. So while those two types of cancer can be very, very common, if they are caught early enough, they can be treated and are less likely to cause death. Melanoma, however, if it is not caught early, can rapidly lead to death, and it can metastasize fairly easily. So melanoma is very, very dangerous, and you should always be on the lookout to see if you see anything abnormal on your skin and to get it checked out right away. So taking you through this here, we have A for asymmetry. So this is looking at various spots that you might find, and here we're looking at a mole, and typically a mole is it has a nice symmetrical boundary. It usually has a typical circular shape, but if you start to see that shape changing over time and it's becoming asymmetrical, then this is cause for concern. Border, B for border, it's when you are starting to have irregular borders, or it looks like it is exceeding its normal borders. C for color, a mole that has more than one color. You're detecting a change in the color. Diameter, it is growing in size. E for evolution, this is a mole that is going through changes, sudden changes in size, shape, and color. So all of these factors that are listed here would be factors that would be cause for concern and needs to be checked out right away. So just be sure to always be on the lookout for these things on yourself, but also, if you see something like that on somebody's arm, then just make a note and say, hey, I think you should get that checked out by a doctor. And typically these things would happen on areas of the skin that are exposed to the sun, but that is not always the case. Sometimes they could show up on the bottom of your foot or underneath the nail bed, so they can show up in some weird spots. So definitely be checking for that. So we've definitely talked about how sunlight can be connected with an increased rate of skin cancer. So there's definitely a link that has been shown to exist between the amount of sunlight exposure to the development of cancer. And it is linked in both melanoma type skin cancers and non-melanoma skin cancers, like basal cell and squamous cell. So in the graph on the left, it's looking at cancer cases, and it's breaking them up by the different types of cancer cases. We see that the basal cell carcinoma has the largest in number, followed by squamous cell, and then melanoma. So basal cell is definitely the one that's going to occur in the largest numbers, and for sure going to be linked to exposure to sunlight. If we look at cancer deaths, we see that melanoma is the one that leads to the most cancer deaths, followed by the squamous and basal cell carcinomas. So while we have larger numbers of these over here, melanoma is the one that's typically the one that's going to be linked up with causing death. In general, the squamous and basal cell carcinomas are going to be occurring in areas where the skin is exposed to the sunlight, and melanoma can be in those areas as well. Although if a skin cancer is detected in kind of like an abnormal part of the body, like it's not being exposed to sunlight as much, then that type of cancer is more likely to be melanoma. There's also data out there that suggest a couple of different things, like they look at how much sunlight have you been exposed to, how long, how often, how long, how many years have you been exposed, and how does that relate to your risk of skin cancer. But they have linked up the idea that, sometimes you have kind of an event where you are exposed to a ton of sunlight and you get like this huge burn, right? We've all had that happen. You go to the beach and you just get completely fried, and it's something you remember for the rest of your life, right? Those kinds of events, you can accumulate DNA damage, and you would have a better chance of having a mutation happen because there's just so much DNA damage happening at that one instance. When we talk about sunlight, we need to recognize that we're usually talking about UV radiation coming from the sun, and that UV radiation has kind of three flavors. So if we look here on this graph, we can see this is where visible light is. Here's the range, 400 to 700 nanometers. And UV light is just right next to it. And they kind of break it out, and they have UVA, UVB, and UVC. So UV is right next to visible light. So I find it kind of odd that like UV is like visible light's neighbor, right? So how bad could it be? I mean, it's not too far away, but it does cause problems for us. When we look at this graph, we're looking at these different wavelengths and then which type of light or types of things that they're related to. So if we're at the bottom of this graph, then we have very long wavelengths, and they would have a lower amount of energy within that wavelength. And as we travel up this graph, then our wavelengths are going to be getting shorter and shorter and shorter. And as that happens, then they can pack more energy into that smaller space there. So at the bottom of the graph, we have longer wavelengths, less energy. Towards the top of the graph, we have shorter wavelengths and more energy. So if we look at UVA, out of these three, it would have the shorter wavelength, less energy. UVC would have the highest wavelength frequency and the highest energy out of those three. This chapter also briefly talks about X-rays, gamma rays, microwaves, but it does kind of focus on the UV there too. But we will get back to some of those other kinds as well. Just summarizing the UV radiation again. UVA had the longest wavelength and the least energy. UVA is going to be the one that is not primarily filtered by the atmosphere, and so it's going to reach the Earth's surface to a higher degree. So when we think of being exposed to UV rays, typically it's UVA that we're being exposed to. If we have a long exposure to UVA, that can cause aging of the skin, and it can actually promote skin cell proliferation, which will become important here in just a little bit. UVB has the shorter wavelength, and it has higher energy than UVA. This is typically filtered out by the ozone layer, so we are not exposed as much to UVB. However, it can cause skin aging, sunburn, and tanning, and it can also cause cancer because it has the ability to create pyrimidine dimers. UVC is the shortest wavelength and the highest energy, so it's the most dangerous. It is completely absorbed by the upper ozone layer, and as long as that ozone layer is there, we will be under good protection. It can be available in some artificial light sources, and it definitely can cause severe skin burns, and of course, it can increase our rates of getting cancer. This slide helps us take a look at the DNA damage induced by UVB specifically. So UVB is the highest energy component of sunlight that reaches the earth. We recognized UVA is the one that we would be the most exposed to, but it doesn't have as much energy in it as UVB. So when we are exposed to UVB, then this creates a situation where DNA damage could occur. Of course, UVC has even higher energy than that, but it typically does not get past the ozone layer. So we would actually be exposed to UVB more than we would UVC. So when we look at UVB, we're talking about how that sunlight comes in through the Earth's atmosphere down to us, and then we are exposed to it. So it's hitting our skin, right? And it's going to penetrate into our skin layer, and so then our, squamous cells, basal cells, those, and melanocytes could be exposed to this UV radiation. And when you look at the mutations that occur, we see that typically pyrimidine dimers occur due to UVB radiation. When we use the word pyrimidine dimer, that means that bases that are pyrimidines tend to form dimers upon exposure to UV radiation. So this could not just be like the TT dimer that we've kind of mentioned before, but you could technically have CC, CT, or TC. In this diagram here, we're looking at a DNA double helix. It's coding for C and G, right? And so we have a strand of DNA that has these bases on it. It's exposed to UV radiation. What happens is we have a dimer occurring between the two C's. So when the cell then goes to do DNA replication, for the side that did not have the dimer formation, it will replicate correctly. It'll have GG right here with its complementary bases CC. On the other side, we'll have our CCs, but they're going to have that dimer between them, and the cell will read it as as a TT, and it'll put the bases as AA. So now we've embedded in a mutation, and after the third round of DNA replication, then this is completely embedded in and becomes a permanent mutation. The cell no longer could detect that it's abnormal. So this is just an example of UV radiation causing pyrimidine dimers in DNA. Now we have talked about this gene before, P53. In this slide, we're talking about the link between UV radiation and mutations in P53. P53 is mutated in a large number of skin cancers, which cause people to look at, can radiation cause mutations in P53? And so we kind of already mentioned that we think UVB radiation causes these pyrimidine dimers. So if we look at skin cancers, would we see a high rate of those dimers occurring, or mutations that are kind of like the downstream result of having those dimers in skin cancer? So we're looking at UVB specifically, and then looking at the P53 gene. So in this graph, they would have taken a large number of cancer cases and done genetic sequencing of P53. And here we're looking at, is there a presence of a CC to TT mutation? And that would be indicative of the pyrimidine dimer. So they do see that mutation in skin cancer at very, very high levels and lower levels in internal cancers, suggesting that that mutation could possibly be due to exposure to UVB within the P53 gene, which possibly was the initiation event for the formation of that tumor. And then when they look at tumors with mutated P53 in internal cancers, we see that they have a higher rate of C to T mutations, not at a pyrimidine site. So that's indicative of them occurring mutations in some other fashion. So this graph just really highlights the role that UVB radiation plays in mutation of the p53 gene, resulting in the development of skin cancer, and that UVB radiation causes that mutation at the pyrimidine dimer. In this diagram, I'm just showing you p53 gene, and this is a lollipop diagram. So every time you see the little line with the dot, then that's the lollipop. And the higher the line, then that means more cancer cases, or more cancers were sequenced and found to have a mutation at that exact location. And so the mutation is listed here for some spots. So we do see that p53 typically has a high rate of mutations in certain areas, and we kind of call those mutation hotspots. So for the full gene, we don't see a lot of mutations in the transactivation domain, but we see a ton in the DNA binding domain, suggesting that this domain is important for mediating its function, and that if we have mutations in that range, then we lose function of the p53 gene. In this slide, we're focusing on how p53 mutation can result in the development of cancer. So in the graph, we're looking at layers of skin cells, and then here they have an exposure to UV radiation, which causes DNA mutations. And so they're indicating mutated cells by the different coloring of the cells. And then number 2, cells with damaged DNA are destroyed by apoptosis. So here with the grayed out cells, we see that the cells had mutations. The cell noticed that the mutation was there. Typically p53 would be activated, and that would cause for the cell to be destroyed by apoptosis. For our cell that happened to have a mutation in p53, then they are protected from this apoptosis, and they will continue to proliferate and divide unchecked. And so this kind of process is what would allow for, preferentially, cells that have a mutation in the p53 gene to develop into cancer. And so this is important. This is why we see so many cancers that have mutated p53, because it creates this position where the cell can no longer detect that it has a mutation, because the thing that would detect that is p53. So if you mutate it, it loses its function, then now it can bypass that checkpoint. Also important to note that UV damage cannot directly hunt and seek out and find p53 and make a mutation on purpose on that gene. As we are being shown here, is that random mutations are occurring in all the cells, but typically the one that has DNA damage on p53 is more likely to be the one to evade apoptosis and to be allowed to continue to proliferate and divide. When we talk about sunlight creating mutations on p53, we can recognize that this could be a tumor initiating event. This is a singular event. It's causing a mutation in a critical gene like p53. So that's our initiation event. Tumor promotion would be occurring if that area of the body is experiencing constant inflammation or other kind of processes to cause the cells to proliferate rapidly, or to induce other DNA damage, or needing to constantly have cellular repair. This could be a tumor promotion event. What we find is that if a person is exposed to sunlight, not only does it, number one, not only is it the tumor initiating event oftentimes, but number two, it can also be a tumor promotion event. So as that person is being exposed to sunlight throughout their lifetime, that this sunlight is causing DNA damage, it's causing inflammation, possibly cell death due to DNA damage. And so this creates a situation where you have a tumor promotion possibility. So in the end, we see that sunlight can be listed as a complete carcinogen because because it does tumor initiation and it does tumor promotion. So our book has made a strong case that sunlight can be harmful and can increase skin cancer risk. It's a known fact. There are a number of studies that have shown this connection. So in general, skin cancer could be preventable since sunlight is the main cause, so a person could avoid sunlight. However, as we know, we all enjoy getting out in the sun. It is good for our overall health because exposure to sunlight can help us increase our production of vitamin D, which is very, very good for us. So we can't avoid it at all times. But we can do a few things. We can wear protective clothes, sunscreen, to help us to minimize our exposure to UV radiation-induced DNA damage. The chapter kind of talks about a couple of other things in relation to skin cancer, one of them being about people's production of melanin. And they do show that individuals that have higher expression of melanin tend to have lower incidence of skin cancer. So that is an important part of how humans have evolved to have protection against the sun by producing that extra melanin. In this slide, since we were just talking about protecting yourself against UV rays, so oftentimes when we do that, we want to use sunscreen. So in this slide, it's showing you the difference between chemical sunscreen on this side and physical sunscreen on this side. So when you talk about chemical sunscreen, it has an ability to block the DNA damage from, block damage that we'd be exposed to from UVA and UVB rays. But what's happening here is it's showing that the UVA rays, the UVB rays, have the ability to penetrate into the skin all the way to the dermis layer for UVA and the epidermis layer for UVB. And that if we use chemical sunscreen, that what's going to happen is that sunscreen is actually going to absorb the rays so that they are not going into our cells and causing DNA damage there. And here are the typical types of chemical sunscreens. If you're looking at physical sunscreens, these have chemicals in them that bounce the UVA and UVB rays off. So here comes UVA, UVB rays, they hit that physical sunscreen and they get bounced off of your skin. So this allows for the blockage so that these UV rays are not getting into the skin. And the active ingredients here are zinc oxide and titanium dioxide. So when you go to purchase your sunscreen, you have a choice. Do you want chemical? Do you want physical? Not saying anything is wrong with one versus the other. I think in general the physical sunscreen does work better and offer better protection. However, if you recognize these ingredients when you purchase these sunscreens, these are oftentimes the ones that look white, like really white when you put it on. And so I feel like many people purchase the chemical sunscreens. Also, if you are sensitive to sunscreens, you could think about that. A lot of people are more sensitive to the chemical sunscreen ingredients and less sensitive to these. But you could always look at what the ingredients are and try to find one that works well with your skin. When you're purchasing sunscreen, you also have some options. And they'll say like SPF 30, SPF 50. So this graph, although it's a little fuzzy, sorry about that, but it's showing you the exposure from the sun versus how many photons enter the skin. So photons would be kind of classified as like those little packets of energy that are traveling in along the UV rays. So it's kind of like a measure of how much of those UV rays got into your skin. So without sunscreen, just for the purposes of demonstration here, let's say you get 100 photons into your skin. If you're using a SPF 30 sunscreen, that's going to give you 93% protection. So in this case, we're down to just 7 photons in our skin. If we're using SPF 50 plus sunscreen, we're going to get 97% protection, and we'll have 3 photons into our skin. So the higher SPF you can get, then the more protection you're going to get. So just to kind of put it all together, we do have a lot of evidence suggesting that UV ray exposure can directly be linked to the development of cancer. We discussed the basal cell, squamous cell, melanoma, and all of those can be attributed to exposure to these UV rays. We talked about UVA, UVB, UVC, and we talked about which ones has the highest energy, the lowest energy, which one's the most dangerous, and also which ones are we most exposed to. You may be aware that there are tanning beds, so sometimes people use tanning beds to have exposure to these UV rays so that they can obtain the tan. So in the past, the tanning beds were advertised as being safe because you're only exposed to UVA and not to UVB or C. However, long term, and then kind of not rapid, but very often exposure to UVA can also be damaging to our skin. So people that use these tanning beds were 15% more likely to develop melanoma. And then if you look at their age at which they started using the tanning beds, if they started using them younger, then they had an increased rate of developing cancer. So if you used it before the age of 35, you have an increase in melanoma risk by 75%. So what this kind of infographic is showing us is that exposure to UV rays can be very dangerous for us. It can result into the development of these cancers. So we should take care of our skin. Here's another little infographic about sunbeds causing cancer. So it's stating the same thing. If you have increased exposure to tanning beds, you have an increased rate of developing cancer. And if you started using them earlier in your life, then you have a higher rate of developing melanoma. However, there are other effects that can happen. You have cataracts, immune suppression, sunburn, and premature skin aging. Now we're going to switch gears and talk about ionizing radiation. Ionizing radiation actually has more energy to it. We can see that it has, here we have our ionizing waves. We see that it has higher frequency and therefore higher energy than our ultraviolet rays that we've been talking about. So it's going to be more dangerous. And it can penetrate further into the body, and it can certainly induce DNA damage. When we talk about ionizing radiation, it has the ability to, very importantly, remove electrons from biological molecules. And in that process, it creates highly reactive ions. And we call these things free radicals. And those free radicals can damage DNA in various ways. So types of ionizing radiation are X-rays, alpha particles, beta particles, gamma radiation, protons. So because these ionizing rays, like X-rays, have higher energy, they also have the ability to penetrate through the body tissues and are more likely to cause cancers of internal cells and organs than, say, like the UV rays. So the UV rays were shorter and they had less ability to get into those internal cells. When we're looking at these ionizing rays, and here we're talking about X-rays, they do have higher energy than UV radiation. As you look at this graph, we see that the radiation dose is down here, and it's being compared to a life shortening, which is kind of an interesting way to put it. So radiation is oftentimes measured in grays. That's the unit. So the higher amount of grays that you have, then the higher amount of radiation exposure there is. And as you increase your exposure to radiation, you have a decrease in your lifespan. You have the other way to put it is an increase in your life shortening. So they are certainly correlated. The book also gives a couple of examples. Here we have 1920s to 1950s. Doctors used it to treat superficial skin conditions of the head and neck for ringworm and acne until it was found that it increased the risk of thyroid cancer in those patients. Also, increased exposure to high dose of x-rays increases the risk of cancer. And so the big example of that is leukemia. So definitely anytime you have a higher exposure rate to radiation, you're going to have a higher rate of cancer. When we talk about radiation, there are 3 types of what we call nuclear radiation, having to deal with the nucleus of an atom. If you remember, an atom has, in its nucleus, it has neutrons plus protons, which make the nucleus, and then we have the electrons that are orbiting around. So when we talk about our different types of radiation, we have alpha, beta, and gamma. Sorry, my signs didn't show up here. So we have those 3 different types. And this has to do with an unstable atomic nucleus, and it has all of this extra energy that it needs to get rid of. When it gets rid of the extra energy, that's radioactive decay, and that's when we have release of that energy, and therefore that creates the radiation. So the overall idea is that you have an atom, and it has a nucleus, and it's unstable. It needs to release this extra energy in order for it to become more stable. When it releases that energy, that gives off the radiation. So radiation can be measured, and so this slide, although a little bit fuzzy, but it does make the point that we do measure in grays. We do have instruments that can measure radiation, but they have the ability to measure how many particles are counted per second, so CPS, and then they can do various calculations to get to grays. When we are measuring radiation and using it to discuss what is the effect of being exposed to that radiation, we set our x-rays as our standard, and then we use this measurement called relative biologic effectiveness, RBE. That's going to tell us what is the effect of that exposure on the biological system or on the body. And we set the x-rays as 1, so that gives us our baseline, and then we can compare the other types of radiation exposure compared to x-rays. And so what this is giving us is the tissue damaging potencies of other forms of radiation compared to that of x-rays. That's kind of the end result here. So equal doses of different types of radiation do not produce equal biological effects, because some exposure to some types of radiation are going to give you more energy than other types. Here we're looking at a table of various types of radiation, and what is their radiation weight factor. So this is kind of like the RBE. So what is the biological effect? Here we have x-rays at 1, proton beams at 2, alpha particles at 20. So we can see the alpha particles have the highest effect on tissues. So we had previously mentioned that we are exposed to radiation just from being here on Earth, and we've already talked about the exposure from sunlight, but here we're talking about environmental exposure to radon. And so radon is a radioactive byproduct from uranium, and it does get released into the atmosphere, but it's also located underground. It kind of seeps up from the earth from various rock formations, and as those radioactive compounds are decaying, then at some point one of the decay products is radon, and so we are exposed to various amounts of radon in our environment. And it's interesting to see the map of the United States, because we can see that the radon levels vary across the different states, and that just has to do with the composition of the ground underneath. So we can be exposed to that radon. It typically comes up as radon gas. It can seep from the earth, and it can definitely cause mutations and cancer inside of our body. So we do care about our levels of radon exposure, and we want to make sure that we can minimize that as much as we can. So as we mentioned, radon is a byproduct of uranium decay. And I have our decay chain kind of chart being shown here. So here's uranium. And uranium will go through a series of steps called radioactive decay, where it releases various packets of energy in a stepwise fashion until it finally gets to a point where it releases all of this extra energy. And it takes forever. It has an extremely long half-life. And then in this process, as it's releasing energy, it's going to change. Here we see a change in name because we're actually changing the composition of that atom. So we have a total change to a different atom when we release that energy. So along this chain, we do make radium, and then we end up making radon, and then from here we have further decay, and we make products like polonium, lead, bismuth, back to polonium and lead again, and then there are more reactions that happen after this. So we're just saying that radon is one of those steps in this process, radon. And then even after you detected radon, then you would expect that radon to continue to go through further decay and create other detrimental radioactive products like polonium and lead. So when we think of this radon, this is occurring due to the radioactive decay of uranium, and it's one of the steps along the way. And it is a gas, and it can go up into the air, and then we could breathe it in. We could also breathe it in as some of these particles are attached to dust when we breathe in our air. Some of those particles that have been detected include polonium, lead, radon, things like that. So as we're breathing that in, we're breathing in those little particles and exposing our lungs to radiation. So it has been determined that exposure to radon is the second leading cause of lung cancer after smoking, and is estimated to kill about 15,000 to 20,000 people each year. So maybe not something that you've heard of too much, but definitely something that's highly important, and maybe we should look at how we can reduce our exposure to radon. So radon can actually accumulate within our own houses or buildings, and this is because we set these buildings on top of the earth, and inside of the earth is that uranium we've been talking about, and we have all of these radioactive decay products coming up off of that. So these little arrows are kind of just showing those decay products coming up out of the ground in various places, and it can, when we have decay of uranium and then eventually we produce radon, that can kind of escape and enter into our buildings in a number of different ways. And they're kind of listed here: the joints, cracks, concrete walls, floors, opening and drains, things like that. So it can kind of accumulate and build up inside of our house. There are ways to release this radon exposure in our home, and there are some different systems that can be put into place to help to reduce this radon situation. So they can depressurize the material beneath the slab by pulling air from under the foundation. So here we see kind of like a structure that's put into the house that allows for that release of that air and radon from underneath the house and allow it to come up out of the house. And we can also test for radon in our home. If you do a house inspection, then typically they would test for radon at that time. And then you also can purchase a radon gas test, and that can allow you to test your own radon, your own home for radon. And it's recommended to do that every 2 years. And then if you do detect a high level of radon, then you could try to have an installation of a mitigation system or determine what your next steps are going to be. I think we are all very familiar with the atomic bombs that were dropped on Hiroshima and Nagasaki during World War II. And certainly events like that, these huge atomic bombs that are dropped, they are going to just rapidly increase the exposure to ionizing radiation in these populations. And so those populations have been tracked, and we can see in the graphs that they do have very high rates of cancer and very high rates of cancer deaths. And we see that there's a ton of leukemia cases and deaths, and for some reason exposure to radiation just really seems to increase the risk of developing leukemia. But we also see a lot of these other cancers have very high case and death rates. Here we have the kind of connection between the dose of exposure to radiation to development of cancer. And so we have a graph that has increasing rates of radiation, and then here we have excess cancer risk per person. So with our solid tumors, we see a steady increase. And then once we get to that high dose, we actually see a decrease and then an increase again. If we look at leukemia, we see kind of the same thing. So it's kind of interesting that at some point we see that cancer risk goes down. And so that is thought to be due to cells being exposed to such a high rate of radiation can kill cells, right? And so it would cause the mutation, but that cell would just die, right? So that's kind of proposed to be the explanation for that, although we don't know exactly for sure. So the problem with ionizing radiation is that it can make free radicals, and free radicals are not good. Free radicals would be any atom or molecule that contains an unpaired electron. And so we kind of see here an example. We have water, which contains oxygen and two hydrogens. And it has been exposed to a type of ionizing radiation. And we see that the hydrogen leaves the molecule. So we have OH over here and hydrogen by itself. But we see this extra dot. That means that the electron was left. So here we have a hydroxyl radical. It's an OH group with one extra electron. And this unpaired electron is what makes this molecule so reactive, because it wants to undergo various reactions to find a home for this unpaired electron. So following that hydroxyl group and that free radical, we can see that it could cause a base alteration by butting up next to a nucleotide and forming a new bond with that nucleotide. And when this happens, this causes a base alteration, and it can also be responsible for causing completely a base removal, and it's also been shown to cause DNA strand breaks. So even just this simple free hydroxyl group can wreak havoc and cause tons of DNA damage. And not only that, but ionizing radiation itself can interact with DNA and induce DNA deletions, mutations, single-strand breaks, double-strand breaks, chromosomal translocations. All of these things result in DNA damage and the possibility to alter a gene that could result in the formation of cancer. When we talk about chromosomal translocation, that idea is that the chromosomes will actually cut and reform. So in this example here, we have two chromosomes shown in yellow and red here. We have a radiation event that causes two breaks in each one of those. When the chromosome goes to get repaired, we have the non-homologous end joining process, and it can actually repair this incorrectly. It can put the red piece on the yellow chromosome and the yellow piece on the red chromosome. And this is what we call chromosomal translocation. So we can have simple translocations, we can have more complex with various mixing between more than one or two chromosomes. So to summarize, we are humans, we live on Earth, we're exposed to sunlight, so we have exposure to ionizing radiation. It's a natural process, we cannot avoid it, right? So we talked about things like sunlight. Sunlight comes in from the sun, and we are being exposed to UV rays. And we kind of talked about the UVA, UVB, UVC, which ones were more dangerous for us, and what is the cause and what is the effect of being exposed to that radiation. We talked about radon, that this is coming up from the earth, and then it can kind of accumulate in our houses, and that radon exposure can increase our overall risk of cancer, and it has been shown to be linked with an increased risk of lung cancer due to the radioactive byproducts residing on dust particles that we breathe in. We have other sources of ionizing radiation, including our medical x-rays, other medical procedures, and that's where we can actually kind of take into account our intentional exposure to ionizing radiation and try to minimize that as much as possible. Well, hopefully we've covered all the different types of radiation and you have a better understanding of your overall exposure, what are the sources of it, and also what is the end product, what's going to happen. So overall it can sound very scary, but always keep in mind that humans evolved alongside this radiation, and we have evolved various DNA repair mechanisms to handle all the mutations that we are accumulating every day. So thank you very much.